Good morning from Dhaka, Bangladesh. I uploaded 3 preliminary videos in Facebook and YouTube about AS and A-level chemistry. Now I plan to prepare a series of lectures on AS and A-level chemistry following the syllabus of Cambridge International AS and A-level chemistry, as well as Pearson Edexcel A-level and AS chemistry. Today's lecture will be on atomic structure. It takes about 3 to 4 lectures of 40 minutes if one teaches atomic structure following the syllabus of AS and A-level chemistry in classroom. And in those cases, one has to spend about 40 minutes for a class. As I will be preparing it for YouTube and Facebook, I planned that the duration of the lecture should be around 20 to 25 minutes. Next slide is about the atomic structure. But to start with atomic structure, we have to say a few words about the history of development of atomic structure. This slide in the screen, it has already been discussed in the short video we have uploaded. Next, Dalton atomic theory also I discussed a little bit, but you see, even today, with Dalton's atomic theory seems to be very useful. In late 1980s, it was shown that atoms are not indivisible and that all atoms of the same elements are not identical. That was the drawback of Dalton's atomic theory. Later, experiments of Henry Becquerel, Thomson, Ernest Rutherford, and their colleagues showed that atoms have a small positive nucleus surrounded by a large space for negative electrons. This positive charge of nucleus is due to the positive particle, which Rutherford called protons. You see, protons are about 2,000 times heavier than electrons. That also I discussed in the last YouTube. But then to become a neutral atom, we have to have equal number of electron, which is negatively charged. The smallest atom are hydrogen atoms, which has got 1 proton and 1 electron. And if we continue, we will see that helium has got 2 protons and 2 electrons, and so forth. One more thing, Thomson atomic model, which was called plum pudding model, which I discussed earlier, but that one has been quickly replaced by Rutherford nuclear atomic model. But then a big problem start up. Hydrogen has got 1 proton, but helium has got 2 protons. But we see the relative masses of hydrogen is 1, but helium is 4 times more than that of hydrogen. That was a problem. This problem was solved by Chadwick, who discovered neutrons, which has got no charge, but it has same mass as protons. The discovery of neutrons solved this big problem, showing that hydrogen atom has got no neutrons, but helium atom has got 2 neutrons. And thereby, helium has a relative mass of 4 units than that of hydrogen, which has got a mass of 1 unit. You know, we used to call proton, neutrons, electrons are fundamental particles. And the fundamental particles means these are the smallest particles. But now, though electrons still is fundamental particle, but protons and neutrons are no longer known as fundamental particles. They are made of quarks. A-level chemistry, we are not supposed to discuss quarks. Therefore, in A-level chemistry, we will have these 3 fundamental particles. We'll discuss proton, electron, and neutron. In this slide, you see the relative mass of proton, charge, and position of these fundamental particles in atoms. So proton and neutron are in nucleus, where electron is in the shells, which I said a bit earlier that a big space is there other than nucleus. Nucleus is the smallest size of the atom, but the atom is big. You can even compare it like this. And if football is a nucleus, then football ground is the atom. Well, here we have 2 very important symbol we call Z represents atomic number. And whereas A in the symbol, you see, in the symbol, which represent mass number. So atomic number is the number of proton. Mass number is the number of protons and neutrons in the nucleus. Therefore, the mass of an atom depends on number of proton plus neutrons in the nucleus. I should have shown here without potassium, this K is a symbol of potassium. Without potassium, a symbol like S, which will represent symbol of element. But I took a specific case here, and I showed here that atomic number to be placed in the left subscript of the symbol and mass number in the left superscript of the symbol. So here the potassium, which has got atomic number 19 and mass number 39. Now we could write symbol of atoms like this. Any atom of any elements, say for example, we want to have boron. So boron has got atomic number 5 and mass number 11. So here, instead of K, we'll write symbol of boron, and here with 5 and here 11. So this is how we represent the symbol of an atom. Why we do so? Because if you remember, Bohr said that all atoms are of same mass in an element. Now you can see that it is not true. If we take here hydrogen as a symbol of hydrogen atom, H, I mean big capital H, and then we have atomic number here 1 and mass number here. If you remember, we said we do not have any neutron in hydrogen atom. So it would be 1 here, 2. Only 1 proton. So it is a 1 here and 1 here. And the symbol of this K would be H in capital H. And thereby we represent the symbol of hydrogen atom. Now, if we keep Z is equal to 1 and change the mass number by say A is equal to 1, 2, and 3, what will be the symbol then? We write H here and then 1 here and 1 here. Then it is, we call symbol of hydrogen atom. But then if it is A is equal to 2, we write 1 here and 2 here. And that is becomes also a nucleus of hydrogen having mass number 2. Similarly, we can have nucleus of hydrogen having mass number 3. And these we call the isotopes of hydrogen. Okay, so can we have mass number 4 for hydrogen atom? Does it exist? No. We have experimentally found that hydrogen has got 3 isotopes. Next one. You see, atoms are very, very small. So it is very difficult, or it is almost impossible to get the mass of an atom by a valence. So what is to do then? So you see, the mass of the hydrogen atom here we show is 1.67 into 10 to the power minus 27 kg. Whereas mass of one atom of gold is about 3.27 into 10 to the power minus 25 kg. You see, even a very small atom or very heavy atoms, we cannot weigh this by a valence. Fortunately, one scientist named Aston in 1990 invented an instrument which is called mass spectrometer. And this mass spectrometer gives scientists to measure accurately, however, comparing the relative masses of atoms and molecules. A mass spectrophotometer is depending on its where you want to use it, have different instrumentations. But then the simple principle in mass spectrophotometer, here I showed the simple principle. We have a heated filament, and then we have to put in vaporized sample, and this chamber should be vacuum, highly vacuum. And then this heated filament, we put the sample in, and this heated filament make this ionized. And thereby we call this ionization chamber. Then positively charged, when we ionized it, it becomes positively charged atom, vaporized atom. We then accelerate these positively charged atoms, and then we have a magnetic field. And this magnetic field separates the mass to charge ratio of the positively charged ions coming, and then we record it, and then put it in the computer, and we can determine the relative masses of different atoms, or even relative mass of isotopes. And thereby we get accurate mass of an atom. Oh, sorry. Yes, there it is. So this weighing problem of this too small atom is overcome by inventing the mass spectrophotometer. But then we have to get number of atoms, and then we must have the standard atoms to compare the mass. And we use carbon 12, you see, carbon 12. Yeah, carbon 12, this is in carbon isotope, and we can also write carbon 12 like this, saying that carbon 12 isotope is being used in standard mass. And this carbon 12 isotope has got exactly 12 unit of mass. So the mass of other atoms is found to be by comparing the masses of carbon 12, and that's what we call it a relative atomic mass. We can see a spectrum, mass spectrum of neon, which what we can see at 20, there is a peak, big peak, and 21, a small peak, and smallest peak, I would say, and 22, a relatively intense peak, relatively high intense peak. But the biggest one is 90.9%. This is relative abundance, and this is mass by charge ratio. And if we take neon in the mass spectrophotometer and do this same experiment, we get a figure like this. What does it mean? Then we have in neon 3 isotopes. One is having nuclear number, mass number 20, another is having 21, and another is having 22, which immediately say us that we can determine isotopes of a element of an atom by mass spectrophotometer. We will see that we use mass spectrophotometer in very many different cases. Okay, now how to determine the relative atomic mass of neon? We will multiply each isotopic mass, that is 20, by its percentage abundance, and then add all together and divide it by 100. And I have done this here. And you see, now we have the relative atomic masses very accurately of neon is 20.2. We were expecting, is it not, that if it is relative atomic mass, we should not have any fractional value. Since we have isotopes and having the abundance different, please note that total abundance should be always 100 or unit 1. So you can see here neon, the highest peak 90.9%, and then the next one 88.8%, and the lowest one is 0.3%. If you add all these three, you get 100. So therefore, we can find out the mass of neon, And since mass of neon has isotopes, therefore we are getting here fractional value of the mass. If we have one isotope containing elements, we would not get this fractional value. Then we talk about relative molecular mass. It is the mass of one molecule, again compared on a scale, and we will compare this with carbon 12, which has got exactly 12 units. Similarly, relative relative formula mass. This is what we call about the compounds containing ions. We can find out its relative formula mass. This relative molecular mass and formula mass are having same symbol. Here we have shown a mass spectrum of germanium and a mass spectrum of lead. You see, I have asked from this picture, we have to see which one is the heaviest mass of the isotope of germanium and also the lightest one. So how can we see it from the peak? You see, this is mass by charge. The heaviest one should be the higher number of peak we are getting in mass, and the lightest one, the lowest one in the mass number is the lightest one. I'm asking here that use this information and find out the relative atomic mass of germanium and lead. What we showed already in case of neon. Now I take these slides, and probably we have finished about 25 minutes or so, and finish this one, this lecture. We will continue the next lecture from here. It's a mass spectrometer is an incredibly sensitive method of analysis, and in which field we use it. If we use it in research, we use it in medical research, monitoring pollutants in the environment, and also detection of illegal drugs in sports. You know, there are some sports people using illegal drugs to win the events of sports. That is a steroid, anabolic steroids. We are taking this steroid, which we call dihydrocordoin, and the symbol is carbon 18, hydrogen 23, oxygen 3, and nitrogen. This is the composition of this compound. We can easily take the mass spectrum, and this is what I show, the mass spectrum of this compound, I mean anabolic steroids. And we can find out the mass spectrum. This is one, and then this compound fragmented. That means it breaks down into smaller parts, and their masses we can find out from this one. You see, when people are taking these illegal drugs to win some events, but they forget this will have many adverse effects. And the adverse effects are heart disease, liver cancer, depression leading to suicides, and women who are using these illegal drugs, they develop masculine features. So it is dangerous. And now it is a banned item, and sportsmen are doped, and people can see the results. And this is the use of mass spectrophotometer in various fields we are talking about. Here I have asked you to find out the relative molecular masses of this banned chemical on the mass spectrum. Show, okay. The mass spectrum of this dihydrocordoin, we are discussing about it. The following question, I keep it, and probably in next lecture I will also give the solution of these questions. You can see the questions are: what is the probable relative molecular masses of banned chemicals on the mass spectrum? Is the probable relative molecular mass consistent with that of dihydrocordoin? Explain your answer. What is the relative mass fragment lost from one molecule of the banned substance, leaving the fragments of relative mass 284? Dihydrocordoin contains a CH3O group and OH group. What evidence does the mass spectrum provide for these two groups? Okay. I have also pointed out or gave some problem when I was talking, but these problems are almost same type of questions you are expecting in the A-level examination or AS level examination. In the next lecture, I'll talk about mode, as well as I'll solve these questions fast and show you a picture of a real mass spectrophotometer. So till today, I should end here, and hopefully we will meet again in the next class within a week. Thank you very much.